Hello and welcome to a new video of the series Tech Bytes. I'm Arnaldo Velázquez, and in this opportunity I will show how to create a polymer model in GEM, the generalized equation of a state modeling simulator of CMG, using the interface of Builder, our preprocessor. Polymers are very large molecules of high molecular weight, constituted by the repeated union of many small units through covalent bonds, and are added to the injection fluids to increase the water viscosity to provide mobility control of the fluids in the reservoir. This is an EOR technique that is called polymer flooding, where the volumetric sweep efficiency is improved, the channeling and the water breakthrough are reduced, all of which increase the oil recovery factor. However, to reach an effective polymer flooding, the mobility ratio that is normally known as M needs to be less than 1, since higher M values leads to viscous fingering and thus create conformance problems. To create the polymer flooding model, I will be using a previously created GEM model. Then the first step that I need to do is drag and drop this model into the builder icon. Then go to the component section and select the process wizard option. In the first step, we need to select the alkaline surfactant and polymer injection process. Let's continue to the next step. In the second step, we need to select the model, polymer fluid. In this step, we need to activate the effects or phenomena that we want to include in our simulation. Let's say that if we unselect all the effects, we still have the possibility to create our polymer model, but that model will include only the polymer viscosity changes with composition and also with velocity in the next step. However, to show all the effects, I will be including one by one, starting with the polymer viscosity as a function of salinity. Then I need to input the initial reservoir water salinity that will be equal to 50,000 ppm in this exercise. Let's continue to the second effect, that will be the reduction of the residual oil saturation due to the polymer capillary number or due to the viscoelastic behavior of some polymer. For this exercise, I will be activating the second effect. Let's continue to the polymer degradation with time. When we activate this option, then we need to input the polymer half-life. That number will be converted in a frequency factor of a first-order reaction, where the polymer is converted to water during time. Finally, we need to include the polymer absorption in the reservoir growth. Let's continue to the next step, where we need to select the components that will be used in our polymer flooding mode. Because we don't have the polymer and the salt component, the process wizard will be creating that component for us. Let's continue to the next step, where we need to input the specific data for relative permeability interpolation. By default, the process wizard uses two relative permeability curves, the first one for the water-oil displacement and the second for the polymer displacement. In this step, we need to input the ratio to reduce the residual oil saturation from the first curve to the second. For example, in this case, that ratio is 0.8. That means that if I have 40% in the relative permeability curve number 1, then my reduction will be equal to 32%. We can do the same for the endpoint of the relative permeability to water. However, I will be using the ratio of 1 by default. Let's continue to the next step, where we need to select the regions where the relative permeability interpolation will be applied. Let's continue to the next step. In this step, we need to input the polymer viscosity versus composition. However, because we are simulating the salinity effect, then we need to input the salinity of the water injection that will be equal to 35,000 and the salinity for the reservoir water that will be equal to 50,000 ppm. We can see a message that the process wizard is taking the lower salinity value to calculate the nonlinear viscosity coefficient for the polymer. Just clicking OK for that message. Now we can input the polymer viscosity depending of the salinity and also of the composition. However, in this step also we can include the velocity effect or shear rate effect on polymer viscosity. For this exercise, I will include the velocity. And again, we can see a message that the process wizard uses the minimum velocity and minimum salinity to calculate the nonlinear viscosity coefficient for the polymer. and also is using the minimum velocity for calculation of the salinity effect on polymer viscosity. Just clicking OK in that measure. Now we can input the velocity or shear rate effect in the first column and the polymer viscosity in the rest of the columns. That is for the first salinity value. To enter the polymer viscosity for the second salinity value, we need to go to the end of the option and change for that value. We can change the polymer composition as we want in the second box here. Also, we can visualize different plots just by changing the variable at the end of the options. Also, we can change the property of that plot. And we can see here the Newtonian behavior of the polymer at lower velocity and the non-Newtonian behavior of the polymer at higher velocity. Just continue with the next step. In this step, we can enter the polymer absorption versus composition, and for that, the process wizard has the option to select different rock type. When we select the different rock type, the rock density is changing. Also, we can input the value directly from lab. We can input the resistance factor value, the accessible pore volume, and the number of polymer absorption versus concentration points that we want to incorporate in our simulation mode. Let's continue to the next step. This is the final step of the process wizard, where we can input the composition of the polymer to be injected and the composition of the salt component. Also, we can select the injector and the date that will be applying our polymer process. Let's click in finish. And we got a message again that the composition of the polymer was converted from percent to molality because we are using GEM. Just clicking OK. We can check quickly the result of this process wizard just by going to the display dataset for section to see the component section inside the dataset. If we go down in the model, we can see the polymer and the sodium chloride component, the molecular weight of that component. Also, we can see the viscosity versus temperature of the polymer. We can see the nonlinear mixing rule of the polymer, the frequency factor for the reaction, and we can see the table of the polymer viscosity versus velocity and the coefficient of the correlation to take into account the salinity effect on polymer viscosity. Just click in OK, then go to the rock fluid section and select absorption component. We have here the polymer absorption versus mole fraction and the maximum absorption of the polymer. Just click in cancel and go to rock fluid section, select diagnostic plots to see how much are the relative permeability curve changing with the polymer. Cancel this window, and the last step is going to File, Save As, and change the name of the model. And with this step, we finish our creation of the polymer flowing model engine. Thank you very much for watching this video, and remember to click like if you consider it. And subscribe to our channel and turn on your notifications so you are informed about our future technical bites and publications.